Electrostatics, Conductors and Dielectrics, series on Electromagnetic Field Theory, lecture number 1.50. Based on electrical conductivity, materials are divided into three categories: conductors, semiconductors, dielectrics or insulators. When conductivity is very high, that material is called conductor. When conductivity is very small, negligible, then it is called insulator or dielectric. When conductivity is in between that of conductors and dielectrics or insulators, then that material is called semiconductors. Conductors, they carry plenty of electrons, free electrons, whereas dielectrics or insulators, they are characterized by absence of free electrons or very little number of electrons. In semiconductors, the number or concentration of charge carriers is in between that of conductor and dielectric. In the present session, our focus is on understanding the nature and characteristics of conductors and dielectrics. As already mentioned, based on electrical conductivity, conductors, semiconductors, dielectrics, this division is there. There is one law. This law is called point form Ohm's law. According to this law, the current density at a point is proportional to electric field intensity at that point. The proportionality constant is conductivity. Mathematically, it can be stated as J equal to sigma E. J stands for current density. Units are amperes per square meter. Sigma stands for conductivity. Units are Siemens per meter. And E stands for electric field intensity. Units are volts per meter. This is very much similar to the Ohm's law we come across in circuit theory, that is V equal to IR. This V equal to IR has another form also, that is I equal to G into V. J equal to sigma E is very much similar to I equal to GV. J equal to sigma E is three-dimensional equation and I equal to GV is single-dimensional equation. Here I is in amperes, whereas J is in amperes per square meters. In place of G, here the place of G is occupied by sigma, conductivity. G is conductance, whereas sigma is conductivity. The place of E is occupied by V, voltage. E is volts per meter, whereas V is in volts. J equal to sigma E is considered to be the most general equation. Now, we spend some time right now on understanding the nature of conductors. Inside a conductor, electric field is always zero. Inside a conductor, charge density is always zero. Rho is zero. E is also zero inside. Charge and field over the surface. These two statements pertain to the situation inside conductor. Over the surface, charge exists in the form of surface charge, sigma, as a result of mutual repulsion that exists between the free charges within conductor. As already mentioned, inside conductor, there exists plenty of free electrons. And there exists repulsion between these electrons. And because of the repulsion, what happens? They try to move away from each other. Result is all these electrons, they move to the surface. So inside, no free charge. It gives rise to certain field E outside the conductor. So third point, as far as third point is concerned, it says that free charge electrons that exist inside the conductor, because of mutual repulsion, they move over to the surface. So inside, no charge, and over the surface, certain amount of charge exists. That charge is in the form of surface charge. Second aspect is these electrons which are over the surface, they create certain amount of field. The field they create inside get cancelled by the field created by the electrons that are over other parts of the surface. This is the situation inside, whereas outside there exists certain amount of non-zero field. The field outside the conductor can be found by this relation E equal to sigma surface charge density by epsilon naught. N is unit vector normal to the surface. Here the surface charge density can be found from this relation minus epsilon naught dou V by dou N. Here it is potential of the body, conductor body. Field direction. The electric field E that exists outside the conductor can only be perpendicular to the surface. It is always normal. The field is always normal. Potential. At various points over the surface as well as inside a conductor, the potential always remains the same. V is constant throughout the conductor. So this is conductor body. Any point over the surface of the conductor or inside the conductor. Any point. At any point, the potential V is constant. If it is not connected to any source, potential is 0. If it is connected to a source, then certain amount of potential, non-zero, exists. But each and every point, it remains at one potential. Relaxation time. When charge is dropped into a conductor, it moves immediately towards surface due to mutual repulsion, resulting in zero charge density and field inside. How fast the charge disperses is related to ratio of permittivity to conductivity, called relaxation time. Here is conductor. When we throw some charge over to the surface of the conductor, because of mutual repulsion, this charge immediately disperses. How fast it disperses? To measure that fastness, one parameter is designed. It is called relaxation time. Relaxation time is given by this formula. Epsilon by sigma here is conductivity. Pressure. The surface of the conductor experiences certain amount of force due to the field on account of the surface charge that exists over other parts of its surface. It can be shown this force per unit area is equal to sigma square. This is surface charge density square by 2 epsilon naught. Direction is normal. What he is trying to tell is, you consider a conductor. This is conductor. Field exists over the surface of the conductor. Now you consider, of course, charge also exists. You consider charge in a small surface area, differential, let us say differential area, there exists certain amount of charge. Now this charge experiences certain force due to the field created by the charge that is lying over other parts of the conductor. See, everywhere charge is there. Here is charge, here is charge, here is charge, here is charge. This charge is giving rise to certain amount of field here, where the differential charge under consideration is located. Because of interaction between that field and this charge, there exists certain amount of force. That force is per unit area. So we call it pressure. That pressure is given by sigma square by 2 epsilon naught n unit vector naught. Now, after understanding a little bit deeper aspects pertaining to conductor, let us move to dielectrics. What are dielectrics? Dielectrics are insulator materials capable of becoming polarization. The basic difference between dielectric and insulator is insulators are not capable of polarization. If insulators are capable of polarization, then they are called dielectrics. Polarization is a significant nature of dielectrics in which positive, negative charges of the material are shifted in opposite direction from their mean position. The term polarization, it has come from the same root from which polarity has come. Positive polarity, negative polarity, from the same root, polarization also has come into being. Before polarization, dielectric is just a dielectric with neither positive nor negative polarity. It is neutral. After polarization, a part of the dielectric becomes positive, another part becomes negative. Remaining part becomes negative. So polarity has been created in the material. That's why it is called polarization. Polarization therefore results in polarity in the material. Dielectrics are associated with large values of dielectric constant. Epsilon r relative permittivity is known as dielectric constant. Dielectrics are associated with epsilon r. They can be in any state, solid, liquid or gaseous, or in any form crystalline or amorphous. Their atomic structure responsible for their electrical behavior is characterized by tightly bound valence electrons, resulting in the absence of free or mobile charge carriers. As already mentioned in the beginning itself, dielectrics, inside dielectrics, free charge carriers, that is electrons, are almost absent or very small, very little. In conductors, free electrons are plenty. In dielectrics, what happens is electrons in their atoms, they are tightly bound to the nucleus. So no free electrons. In perfect dielectrics, which do not exist in real world. Here, we need to understand two terms. Perfect conductor. What is perfect conductor? Perfect conductor by definition is one for which conductivity tends to be infinity. Then what is perfect dielectric? Perfect dielectric is one for which conductivity is zero, or tending to zero. Perfect conductors, perfect dielectrics, they do not exist in the real world. What we have or what we can have is good conductors. Good dielectrics. Good conductor is one for which conductivity is very high, whereas good dielectric is one for which conductivity is very low, almost zero. Now, in perfect dielectrics, which do not exist in real world, free electron content is nil, resulting in zero conductivity. However, in practical dielectrics or in the real world dielectrics, free electron concentration is small, not zero, resulting in very small amount of non-zero conductivity. Dielectric nature of materials is characterized by permittivity, epsilon, and conductive nature is specified by conductivity, sigma. The ratio of conductivity to permittivity is considered as an indication of electrical nature of materials, whether conductive or dielectric. Most of the times, after taking frequency also into account, the ratio sigma by omega epsilon. Sigma is conductivity. It characterizes the conductive nature, whereas epsilon is dielectric nature. This ratio sigma by omega epsilon, it is called dissipation factor or loss tangent. Equal to 1 is considered as dividing line between conductors and dielectrics. If this is more than 1, sigma by omega epsilon is more than 1 means it is considered a conductor. If it is less than 1, it is dielectric. For good conductors, it is very, very large when compared to 1. For good dielectrics, it is very, very small when compared to 1. There is a classification for dielectrics: linear, non-linear. This is one classification. Homogeneous, non-homogeneous. Another classification: polar type, non-polar type. What is linear and non-linear type? Within dielectric, if the ratio of displacement density d to field intensity E is constant, in fact, d by E, it is epsilon, permittivity of the medium. Within dielectric, if the ratio, irrespective of magnitude of field intensity, is constant, within dielectric, if the ratio is constant, then the material is linear. Otherwise, if the ratio is dependent upon field intensity, then non-linear. Homogeneous dielectrics are characterized by uniform nature of properties throughout the material. In case of non-homogeneous dielectrics, properties vary from point to point. Uniform, homogeneous. Polar, non-polar. In polar dielectrics, the positive and negative charges in the molecules remain shifted permanently from their mean positions, resulting in the existence of several pairs acting as dipoles. In general, these dipoles are oriented randomly within the body of the dielectric, and application of electric field tries to align them in one particular direction. In non-polar materials, dipoles that do not exist earlier come into being when external field is applied. Now, how polarization? What is polarization? See, inside dielectrics, like any other material, there exists atoms. Atoms means nucleus surrounded by several electrons, electron cloud. In metals or in conductors, what happens is some of the outer band electrons, they get detached from the atom and they keep on moving in a random manner within the body of the conductor. But inside dielectrics, what happens is all the electrons, they are tightly bound. Inner electrons as well as outer electrons, they are tightly bound, and they are somewhat symmetrical, almost symmetrical within the atom. Now, when this material is, dielectric material is placed inside an electric field, let us say electric field is like this. When the material is placed, what happens? Under the influence of the field, nucleus, which is positively charged, it tends to move in one direction, whereas the electrons tend to move in the opposite direction. Net result is the atom as a whole is symmetric in all aspects earlier. Now it becomes somewhat asymmetric. Now the shape of the atom is like this. Nucleus is shifted in one direction, whereas electrons are shifted in the opposite direction, asymmetric. So now I can say, one can see that right hand side, this kind of thing happens as far as all materials undergo this kind of change. Net result is nuclei in the material, they got shifted in one direction, electrons got shifted in the opposite direction. Net result is, at one end we have accumulation of negative charge, and on the other end we have accumulation of positive charge. So the body earlier was neutral without any polarity. Now the neutral body is positive on one side, negative on the other side. This phenomena is called polarization. Now this is what I want to share with you regarding conductors and dielectrics.